Alright, so we are trying to find solution to the problem of that we identified in the previous slide, which is direct access table, which is effectively an array. The first problem is a problem that the keys may not be integers, whereas arrays or simple access tables use integer keys. The solution to this is to use a method called prehash. In this method, you map the keys, whether they are strings or any other data type, to integer values. And this makes an assumption that the keys are finite and discrete, and in this case you can map it. So you have something like this. You have a way to map. For instance, you have a key called x, y, z. So you have a function that maps x, y, z and gives us let's say 20 or whatever it is. So some applications try to implement the prehash method that tries to map keys to integer values, but this makes an assumption which might not always be practical. The next method is to reduce space, because we say that simple access tables consume a lot of space. You need to reserve a whole lot of space beforehand. So how do we solve this problem? And that is where hashing comes into place. We need to reduce the universe of all keys down to a reasonable size m using the method of hashing. So let's illustrate it. This is our hash table. How many slots are there? So we have 0, 1, 2, 3, 4 up to m minus 1 slot, because we have 0 here. Take note that these numbers here might not actually be sequential numbers, but simply they are just numbers, or they are just keys. Alright, so let's see how it works. This is the universe. We have this bigger circle is the universe where all the keys are. Let's take, for instance, this universe may be keys of all positive integers, right? Good. And this subset here is all the items or the keys that are available to be hashed, right? So K1 to K4 means that we have 4 keys, and M stands for the size of the hash table. So what is going to happen is something like this. If we want to place this K2 into this hash table, we pass it into a hash function H. So H is a hash function. So when we pass this key into a hash function, it gives us a value of 0. And then we store K2 into this place. The same thing happens for the next one. When we pass K3 into the a hash function, maybe it gives us a value of 2, and then the values that we get from the hash function tells us where to, or the address where to store the values we have. So we place K3 in here. Okay, so and so on and so forth. But problem might arise when we hash 2 items and they hash into the same hash table, into the same position in the hash table. And what do you think this is called? Yes, you guessed right. This is called collision. And this is formula for collision. Collision occurs if HKI equal to HKG and KI is not equal to KJ. So take pen and a paper and write this down. So this is what happens when collision occurs. And granted, clearly you cannot store the 2 keys into the same position in the hash table. It will never work. So something has to be done to solve the problem of collision, and hashing has a method of solving the problem of collision. So how do we resolve the problem of collision? We can resolve the problem of collision using either of 2 ways. One, we can use chaining, and 2, we can use open addressing. Just keep this in mind, or make note of it if you have a pen and a paper. Collision in hash tables can be resolved using chaining, and open addressing. So we are now going to discuss hashing with chaining, and then after that we discuss open addressing. So what is chaining? Chaining is the simplest method of resolving collision in hash table. So let's start with this example. We have this hash table and we have multiple items hashing in the same location. And what we are going to do to solve it, all the items that hash in the same position, store them in a linked list. I don't know why I can't draw straight. Let me try a second time. So all the items that hash into the same position, store them in a linked list. That's what you are going to do to solve this problem. So let's see how it goes. Let me display my diagram again. So this is the universe. These are the items. And what happens is K1 and K2 hashes into this place. So you move them out of this place and then put them into a linked list. So in this case, what we are going to have is that instead of K1 being inside this position, you place it here, K1, and place K2 in here. Right? I hope it's very clear. So in this case, any item that hashes into a place, just place it in a linked list. So what happens is this hash table will contain only addresses of linked lists. Of course, some locations might actually be empty, so we can have empty slots here and there. Nothing is here, and so on. So, but wherever we have an item, simply place the key in there in a linked list. So that is how we resolve collision with chaining. Alright, so we need to know, actually be able to analyze how good chaining is. So in the worst case scenario, what is going to happen is that many items will be hashing into the same location. So let me display my diagram again. K1, K2, K3, K4, all of them is going to just hash into the same place. And in this case, it is still solution to the problem. No two items will be in the same K2, K1, K3, K4. And then another element comes, you still create another item in the list. So this is worst case scenario, is that everything will go into this place. So this is worst case. So when it's worst case scenario like this, then performance will be order of n. So just to tell you a little bit about this, order of n means that the performance will be proportional to the number of elements. So let's say performance will be proportional to the number of elements. So it increases as n. The performance decreases as n increases, or search time increases as n increases. All right. So the next thing we are now going to discuss is simple uniform hashing. I want you to take some time to get your head around what we've discussed so far about hashing with chaining, and then we now move to simple uniform hashing. I'd like to continue with this in the next presentation. Remember to subscribe if you've not subscribed, and also let me know something you would like to learn, and I'm going to explain it to you.